好，那刚才有同学跟我反映，他是没有听不懂中文的，好，因为有教文生之类的，好，所以我们要这节课我就开始用英文讲，好，这个我们试着听一下，好，懂就是再来问，或者是看一下课本，好，或者说稍微看一下讲过复习的类似，哦，就是看，因为我不知道大概吸收效果怎么样啊，我也很久没有跟你们上课，哦，所以我只是看啊，所以因为有同学反映，然后所以就用这个用英文来上课，好，好 ，OK， 大家talk about the next topic 啊 ，binary arithmetic about the operation other than decimal based the number system because there is a pointer right here, this right here. The reason we have to understand for example here primary arithmetic because internal computer they perform the operation on primary mode. So we have to understand how they perform binary arithmetic operation. Okay, so let's look at this point. The arithmetic operations in digital systems are usually non-binary because design of logic circuit to perform binary operations is much easier for this. That's the point I mentioned before. If we design a decimal system, the circuit will be very complex. It will be easier to design circuit binary mode. Okay. So here is binary addition. It's a variable or the coding rule. The addition table. This how we perform in binary binary system 0 and 1 for example 0 plus 0 is equal to 1 1 is the result for this table 0 plus 0 is equal to 0 0 plus 1 equal to 1 so in this case 1 beta 1 is equal to 1 0 in practice we just mention to this 0 the result the carry 1 to this column. We define this is there is a carry in the circuit design. So the result here is this 0 and have a carry bits for this column. Okay. For example, we had a 30 base 10 and 11 base 10 in binary. How we can perform such addition. So the 30 of the base 10, we have this expression. How can we obtain this expression? We have to mention this time. Last class we will understand how 30 become this expression. So let's skip this step. And the 11 will become this expression. So there are two expressions in binary. The greatest two. And how we perform the addition. See this is right here. So if you obtain this binary expression, enter this significant digit first. 1 plus 1. We got 0 right here. So we put 0 here, and there is a carry. Then put the carry. So we put the 1 here. This indicates there is a carry. Last stage, we have the addition result that will carry. There is a carry right here. So there is 1 indicates there is a carry. Still perform addition for binary number 1 plus 0 equal to 1. And this 1 plus this one. Okay, we get 0 carry. there's a 0 right here, and there's 1 indicate the carry, the last part. Okay, so this process continues, and on 10 up to here, there's a carry 1, and there's a 2, 1 each number. So 1 plus 1 of 10, 0, and 1 carry. And the 0, add this one, get 1, and we have carry 1 right here. So, and the other digit 0, 10, 1 right here. This is the final result. Okay. So this is the example of the addition. So next, we talk about binary subtraction. Okay. This is a subtraction table. 0 minus 1, minus 0. We have get 0. 0 minus 1. We have that one, but we have borrow 1 from next column. Also, 就是介意一个位元到就下一个位元介意的意思。Okay. The borrow 1 from next column. Okay. So 1 minus 0 get 1. 1 minus 1 get 0. That's this is the table for subtraction. Okay. So right here we see the example to see how we can perform binary subtraction for two numbers. Okay. So right here there's number 1 1 1 0 1. There's 1 0 0 1 1. Okay. So we perform the subtraction for right here. 1 minus 1 from the table we get 0. Okay. And 0 minus 1 will get 1. But then we have a bubble. Right? So 0 minus 1 will get 1. And there is 1 right here. This one indicates there from the last card subtraction. Okay. So this one is a bubble. And this one is a bottle. It is equivalent to minus 1 for this column for subtraction. This one means borrow the last column, but this one is equivalent to minus 1. Okay, so right here this is equivalent to minus 1 right here. So we perform the subtraction in this column. This one subtracts to minus 1 will become 0. Minus 0, okay, 0 here, so we're going to have 0 here. Okay. And this one, this column is 1. And the next number, the digit is 0. Also, 1 minus 0 will become 1. Okay, on the table. Okay. And this one, 1 minus 1 is 0. From the last slide, we showed the subtraction table, so this one becomes 0 here. So this is the final result. So wherever you find there's a power bit, it's minus 1. So it was easier to understand how to perform the subtraction. Okay, so in this case, practice again for this example. 0 minus 1 equal to 1, right? And there is a borrow. So there is a borrow bit equal to 1 right here. And again, this means minus 1. This means minus 1. So in this case, 0 minus 1 equal to 1, right? And there is a borrow also. There is a borrow bit right here. So 0 minus 1 equal to 1. And this one minus this one will become 0 also. Feel the digit 0 right here, but there is a borrow. Okay. Similarly, for the next column, this is minus 1, this is 0, and 0 minus 1 will become 1. So there's here, but there's 1. So the serial process continues. So let's skip the other process. So you can a similar concept to see this example in the case. So let's just skip this detail. Okay. Okay. In the above, we see the binary subtraction on S. We talk about binary location on 乘法. Okay. So this is a location table. So 0 multiplied 0 equal to 0 multiplied 1 equal to 0, and so on. So this is a location table. Okay. And how we perform multiplication binary number system? We see this example right here. And we multiply 13 by 11. The 13 and 11 will be both base 10 number. Now, the expression vary. This is the same as before. So 13 equal to this expression. This 11 is equal to this expression. Then we perform the multiplication for these two numbers. So first we this one to multiply 1, 1, 0, 1, we obtain this expression. Okay. Why this one multiply this become this expression? Because we use multiplication table right here. 1 multiply 1 equal to 1, 1 multiply 0 equal to 0, so on. So we obtain this 1, 1, 0, 1. Okay. The next bit is 1. Again, 1 multiply 1, 1, 0, 1. We obtain this expression right here. Again, we use this multiplication table for this expression. The next bit feature is 0. And 0 multiply this number will become 0, 0, 0. This equation whenever it requires 0 multiply 0 or 0 multiply 1 all equal to 0. So this one right here. And finally, the digital multiply this number and this expression. Got this partial result, we have to get to obtain this final result. And how we obtain this final result? This one we can use the addition table to obtain this addition result. This column 1 and the 0, 0, all 0 here obtain 1. And this 0 and 1 of the other 0 obtain 1. So we see to add all the columns together. Obtain this 0. There will be no problem. But to see this case, if we do the similar way again with a different number, for example, this we try to multiply 50 by 30 by 3. The 50 binary expression will become this 1, 1, 1, 1, 1. And the 30 binary expression we obtain is 1, 1, 0, 1. Okay, we try to multiply two numbers, then we do it similar way. This is the reverse 1 multiply 1, 1. Obtain this partial product for this digit. 0 multiply 1, 1 get this partial result, and the third one multiply this one get this result. So there are 4 digits, and there are 4 partial products. And then we try to add these together. There is one problem, because there may sometimes we made these all partial product equal to 0. And there are 4 1 and time we try to again. And in this case, add 0, 0 equal to 1, and add 2, 1 will get 0, 1 carry. If we add 4, 1 binary together, the label right here, we cannot follow any one word, right? 然后再是把这个，比如说有4个4的话，你加起来用。然后说那个开场往出弄。Too many ones together, then we cannot use any rule right here. Okay, to compile we use all partial product together to add 1 all 1 column at a time. We can follow any rule of the table. So we have to perform it this way. This will obtain first partial product, and will obtain the second partial product. We have to perform addition first. To avoid the case I just mentioned, there are too many ones, and we can follow it. So in this case, in this way, there are 2 expressions right here. And this digit 1 multiplied 1 obtain this first partial product. This 0 multiplied 1 you have obtain this second partial product. And we add this partial product first to obtain this result. And these 2 partial products together, they can obtain a better rule, addition rule. There is no problem right here. So we have to this partial product, we have to obtain 0, 1, 1, 1. And obtain this expression, then we obtain the third partial product. This one is the sum of the first 2 partial products. And get the third partial product and get the more addition. Then use the rule addition table to obtain this result. No problem. Otherwise, there are too many ones. Okay. So obtain this one, we to add the fourth partial product. That which is obtained from this one, this one, 1 product, 1, 1. This one, add these together, get the result. So we have to perform it this way because you upgrade compute inside in this way. Okay. Okay. This talk about the division. So in this example, we divide 145 less than by 11. So how we can work binary? So this we are seeing this right here. And then 145 is equivalent to this version binary. So I just skip it step. Skip it just try to divide. The rule we have just mentioned. That's case. Okay. So let me just skip the step. 145 will equal to this expression binary, and this 11 will have this one expression, and then we perform the binary division. Right here. So in this case, we check that 1001 cannot be divided by 1, 0, 1, 1. So we'll start from here. This digit. So we have to start from here to do the division. So in this case, this the one function right here, and as a base 10 system. So this one multiply 1, 0, 1, 1 will obtain this result here to do the subtraction 1, 0, 0, 1, 0 to subtract 1, 0, 1. Okay. So these two numbers will perform binary subtraction, and we obtain this 1, 1, 1, 0. Okay. And 1, 1, 1, 0 compared with the 1, 0, 1, 1. Which is larger. So it's larger, so we can perform the addition. So put the quotient 1 right here, 1, 1, 0, 1, 1, and this one. Okay? And then these two numbers perform subtraction, obtain this one, 1, 1, obtain the 1, 1, get a 1, 1. Okay? And this we bring down this 0 here, get the 1, 1, 0. 1, 1, 0 is smaller than 1, 0, 1, 1. So the quotient right here, there. Okay? So 1, 1, 0 cannot divide by this one. The quotient is 0. So we bring down this multiplication 1 right here. And this number is larger than this one. So the quotient is 1 right here. So again, 1 multiply this one, obtain this result, and then we perform the subtraction. So we get this method. Okay, that's the derivation of the primary number system. Okay. Okay. Next, we talk about the representation of negative number. 就是复数 of negative, 就是 the number which is smaller than 0. Okay. So in the system, in the computer system, how we can perform is to represent this negative number, and how they can that which is what we use for perform do the subtraction or addition like the internal computer will see the benefits. Okay. So in the first point right here, it mentioned in most computers, in order to represent both positive and negative numbers, the first bit in the word is used to as a sign bit. For example, there is 4 bit here. This expression is 4 bit. The first bit is this one, or this one. This one. This first bit will called a sign bit. The first bit in the word is used as a sign bit, which means the sign bit will indicate that this number is positive or negative. For example, 0 means that the number is positive. And if the sign bit is 1, it will indicate that this number is negative. Okay? What does it mean? You will see the detail following variable. Okay? So with 0 use for plus, 1 use for minus. That's a mentioned equivalent. Okay. Any base word we can represent any one of to the power n minus 1 positive integer or to the power n minus 1 negative. This number of the positive integer or negative integer the system can be represented. For example, if there are 4 bits, that means n is 4. Then we can represent 2 to the 4 minus 1 equal to 3. Okay, so 2 to the power of 3, 8. So we represent the 8 positive integer and the 8 negative integer. If there are 4 bits. Okay. So if what I mentioned, if you you are see this table, you will become more, you are easier for you to understand what I'm saying between this point. Or if you do not get what I'm saying, this one will vanish. Okay, the third item, you mentioned several differential implications of negative number and positive. It means there are maybe more than one method negative number, positive number. It means that the system may be just one method. We are a couple system. You can present a negative number or positive number. For example, the first one may be called sign negative. That's the method 1. Okay, or 2's complement system or 1's complement system. That's a different method to present a negative number, but without different. Mean the same thing. For example, if you want to represent -1, the 3 system will have a different expression. Okay, and there, if we want to perform addition or subtraction, they will have different. Do the circuit design because they are different systems. The property will be different. Okay. So, how they perform this addition? Subtraction or this, example, what's complement, what's complement or sign or negative, we'll see about. Okay. The fourth item, the design of logic circuit to do basically with sign and negative binary numbers is overload. It means you use this method, it will be highly complicated to do the logic circuit design. So we won't use this system to prevent negative. We'll use 2's complement, 1's complement. Okay, that's how this is try to say, try to mention. Okay, so in case if you use this one, you will be helpful. It's not easy design for the circuit, to different circuit. Okay, so next we will try to understand what is the 1's complement system. Complement system. And this table represents sign binary integer. Sign binary means the first bit will indicate negative number or positive number. All these 3 systems, sign, negative, 2's complement, positive. All the first bits will indicate this number is negative or positive. So we'll see this one. This one will be the number base 10. Okay, decimal number here from 0 to 7, positive 7, and this one is the 0, -0, -1, -8. Okay, and if we use positive integer or all system. However, maybe one of these, all expressed this way, positive number. The first bit will be all 0, the other one will be 0, 0, 1, 0. Okay, you can just wait it out, with the sum, and you will find on the same file the binary expression. Maybe you have it, but you get it through this. Already so it's really scale. So all this one will be a positive number for you. 7. And for these three systems, they have different results, negative number. Okay? So for sign and negative, we quite easier to get this conversion. Find the first bit is 1, or is equal to 1. This is negative. And the remaining 3 bits for the same here. Okay? For positive 0 is 0. Next, negative 0 is 1 of all these 3 bits are equal to 0. The minus 1, you will see just for negative 1, put inside the 1 by here. Remaining bits by the same, the positive number, all the same right here. You see the same, just put the 1 right here. First bit indicate it's a negative. For sign negative system, you will be easier to understand how we can use this expression. However, for tooth complement, not quite straightforward. Maybe I mentioned the easier one, tooth complement system. This one is an expression for tooth complement. This one many for -1, -0, -1, up to -7. All these expressions. So you figure out how this one convert this negative number to this expression. And you figure out how they can get this one. Just give you 5 seconds. I'll give you an answer. Okay. So anyone know how they do this making for negative number? Any student have figure out how we can convert this negative decimal number to this must convert expression. 有没有人知道？看出来吗？好。
1跟0调换。
对，没错。That's right. Just what's common just is equal to, but then have a arithmetic expression. There's an arithmetic expression for the define definition of what's common. Then the next good way. So you are easier to use the I check. Just this mapping is just use positive integer. 0 become 1. This 1 become 0. This is 1 will be 0. This is 0 become 1. That's a 1 cover. How what's the definition of this result? That's quite easy. So, that's what's common definition for the negative number. Just 2 to the power n minus 1 to trigger n 1 equal to minus n. That's the definition. So by this definition, this expression is 1, 1, 1, or if n is 4 bits, then this value is 1, 1, 1, and all ones. So for all ones to be subtracted by n, so that's what we convert 1 to 0 to 1. That's a reason. So that's the become this result. Okay. About the tooth complement. Tooth complement, if you obtain the ones common, plus 1, do I have this result? But this result plus 1 becomes 1. This one, you plus 1 will become this one. This one plus 1 will become this one. That's the tooth complement. The definition of the tooth complement for the negative number. Okay? So, what's common is the definition next. This definition just write in the last word. Okay. So this put the power n minus 1. Okay, this expression, and you to subtract the positive n, what becomes this negative n, the value of negative n in terms of expression for the one's complement on this definition regarding one's complement. Regarding the two's complement, let's say this one, this subtract this one. And in the last you can say this result 2 plus 1 will become this one. That's the same, because this one plus 1 will become 2 to the power of n, right? I mentioned one's complement, the result of one's complement, and you add 1 to the result, you will get a two's complement negative number. So add 1 will be equivalent to the one's complement, this expression right here plus 1 will become 2 to the power of n. So two's complement here, you can find the expression right here, this one, subtract this one, to get the two's number. Okay, so that's why I say if you have n one's complement, and you add 1, you'll get this expression. Okay, so there are 3 different representation to represent the negative number. This one we seldom use it because we have mentioned it's a awkward, it's a circuit. These 2 will be easy. Okay. So actually, you understand how obtain the negative number for one's complement or two's complement. We see some example for the conversion, and then we find their addition, subtraction, how they relate to the circuit. Okay. So in one's complement, the negative number of the positive integer n with n bits, what else? You represent by this. One's complement will become this expression. Okay, that's just a mentioned before. Okay, so that's a definition. To form the one's complement, to simply complement n bit by bit, by tracing 0 is 1 and 1 traced by 0. Just a simple straight answer to convert 0 to 1, 1 to 0. That's the one's complement system and negative number. Okay. So for this number, we try to represent minus n. This n bar is minus n. So how to represent minus n in one's complement system? Just write the positive number expression here. 0, 1, 0, 1, 0, 1. And we convert 1 to 0. And 0 to 1 will become minus 1 for the one's complement expression. Okay. So this one 0, 1, 0, 1, 0, 1 become 1, 0, 1, 0. That's minus n. The expression for the minus n in the one's complement system. Okay. this example. For the tools cover, just to perform this subtraction, to the power of n from here and subtract n, we obtain this expression, and this expression will become the negative number for the tools cover. Okay, and so we can you can do the subtraction to get this one, or just the method I mentioned to perform one's complement as the first to get this one plus one, get a result and plus one. After you obtain the one's common result, and you get the one, you get this expression, and this expression will be the tools common result. Okay, check. These are the same like this one. Okay, that's this is the definition. These two are original definitions. These are for one's complement, this for the tools complement. So you can do this first, and the other one will become this definition. So we get this one, and plus one, we get a result. This one will be the same. Then you can do the way you want. Get a quite a medium. Get used to. Well, then it's covered results. Okay. So in the second point right here, the tools complement can be formed by complementing and bit by bit, and then adding one. So the sentence right here just is like just out of and will obtain the one's common result if one will get tools common result. Okay. And this one is another way. The easier way to form the tools common n is to start at the right and compare all the bits to the left of the first one. What does it mean? You start the first. This is a positive way. You start from the right. Start at the right. And compare all the bits to the left of the first one. So from the right is this one, and you find the first one here, and compare all the bits left the first one. So this becomes 0, 0 become 1, 1 become 0. That's this sentence about. So maybe I check if there are any example. Maybe you may feel more much clearer to how this point right here. So for this one, you try to find the tools common. Say, find the first one from the right, and common all the bits. So it will become the 1, 1, 0, 1. This is positive 3 and minus 3 right here. 1, 1, 0. So, 1, 1, 0 right here. The sentence just mentioned, you start from the right. So we start from the right, we find the first one. This is the first one. And complement all the bits. So this this one keep it. And remember the 0, 0, 1, so you cover all this 0, 0, 1 to 1, 1, 0, so it's a 1, 1, 0. So result. Okay, that's the dimension. That's the method. The sentence just mentioned. Maybe we use this one. 0, 1, 1, 0. We start from the right. This is 0, so skip it. This is 1. Okay, that's a 1 because we got from the right. So 0, 1, keep it. So we can find this is 0, 1, keep it. And the remaining 2 bits of 0, 1 will convert it. So you become 1, 0. So you find 1, 0 right here. Okay. So in this case, we start from the right and find the first one. The first one, this is second bit. So 0, 1 will keep it right here. And cover all the main bits. 0, 1 here will become 1, 0. So you will see 1, 0 right here. Okay. You can practice the other step just mention 2 or 3 cases that you understand what is mean in that sentence. Okay, that's more rigorous definition to find what's covered or what's covered for the negative number. Is real good. Next. We perform addition for this common number. The first point right here, the addition is carried out just for all the numbers across. We perform the addition just like the addition, but the first point right here, the addition is carried out for all the number or the positive. We treat all the number of positive to perform the addition. The addition rule is just the addition table. We just show a couple number. Treat all number of positive to perform addition. It's quite not a long step. You may see about simple. We treat all number like a positive, no negative or positive. Okay, that's the first point. And any carry from the sign addition is ignored. The result if there is sign will be ignored. Okay. And the third one, the overflow occurs when the sum is equal to and the larger to the power and to and this or that. That means if we perform addition, if possible, after the addition, the result will be greater than the number we can replace. For example, the number original has 4 bits, but the two number of 4 bits, it may require 5 bits, but we only have 4 bits. So it means the overflow. That's the result of the number which the bits, the number of bits we have quite enough to represent the final result. We call it final form. Okay. What does it mean or how we perform circuit? We will tell you find the whole sample. Okay. That's just you. First you try to understand what it also that's a result. The required number of bits is the more than you have the system. Okay. So these are a couple of examples to explain how the above sentence paragraph try to mention. Okay. The first one, the addition of 2 positive numbers, and the result is a smaller than the power of the n-1. Okay. There are 2 numbers. One is plus 3, and the other one is plus 4. So these are the base 10 of the decimal system. Okay, look at the end of the numerator. If we perform in binary, you can see this 0011 is a binary expression for 3, and the 0100 is for 4, and we add the 2 together. Let me just very quickly to see how they get it done. 1 plus 0 become 1. Okay, we use the table just mentioned. And 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. Okay, so this will be the result. Okay, the result is 7. That's 7 is smaller than these are 4 bits, and the 3 the n is 4. 4 minus 1 is 3. The power of 3 is 8. The 7 is smaller than 8, so it's there is no overflow, so it's fine. This is correct answer. Okay, and we addition of a two number, but in this case we have the overflow. You see the result right here. Now 5, the positive 5 have this expression, positive 6 have this expression. Then we perform binary addition. We have according to the table, we have this result. Okay, 1 plus 1 become 1. 0 plus 1 become 1. 1 plus 1 become 0. Okay, and we have a carry. So 1 plus 1 is 0. We have carry. Now carry means 9 plus 1. The plus 1, add 1, and put add 0 and 0 become 1. We have this result. Okay, according to our table. Okay, and this one you will find in the in a system. Remember that first bit means what does it mean for the first bit? Means a sign bit. Okay. The first bit is 1 right here. It means a negative. So this we have if there is a negative number for this system, we add these two numbers together, we will get this result. But this result means a negative. Wrong answer. So in this case, the wrong answer is due to overflow. Okay. So the wrong answer was overflow because we add these two numbers together. We have 11 decimal system. The 11 is larger than 8, right? I show you right here. If the number add together, which is larger than 2 to the power n minus 1, there is overflow. Okay, so 5 plus 6 will become 11. 11 is larger than 8. So there's one overflow. Okay, because 11 requires 5 bits inside it. So a real system we only have 4 bits. Not not. So there's overflow. Okay, in this case. So the next one, addition of positive and negative. So the first rule tell you just perform addition, just like positive. You see this case, so why did it already? This expression 5, this expression is 6. You can check. This for those complement. This one is minus 6 for this complement expression. Check it right here. Minus 6 for those complements that I have this expression 1, 0, 1, 0. Okay. So 1, 0, 1, 0 is is the expression of -6 for tooth complement system. So write the equation right here. And we perform the addition just like these two numbers are positive. And we perform this addition. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. Okay? So this result is this one plus this one. Okay, this result. This one right? Fine. You can check. This 111 is 111 all ones. 4 bits are equal to 1 right here. And they equal to constant. What's common system? So we perform addition for these two numbers to get a result. We got the very rate. We don't need to perform any additional operation result. Okay. So just treat these two are all positive for addition. The rate the result will be the correct answer. Okay. Let's see the other four cases. See which one will have contain eraser, or the other one will have an overflow situation. Okay. In this case, okay, these are that's different from the last case. Last case, the negative have a larger magnitude. Okay, in this case, the positive number have a larger magnitude. Okay, so -5 have this expression, right? Expression, and plus x have this expression right here, and we perform the addition the rate, and we obtain here. And for the tooth complement, if there let me adjust it bit by bit first to see the result, how we have obtained the result. 1 plus 0 is 1, 1 plus 1, and 0. And carry, right? So we have carry right here. Okay. And 1 plus 1 is 0. We have carry right here. And the carry means positive. Plus 1 right here. So it's a plus 1, it's a plus 1, plus 1, plus 1 is 0. We have carry. So we obtain 0 here. And we have carry right here. Okay. And this 1 is carry. Total plus 1. And this is also plus 1. 1 plus 1 is 0, and we have carry. So 0 here and 1 carry here. Okay? For this result, if there and carry, that's really for instance, when the carry from the inside bit is 0. So for the only 4 bits, there carry in the fifth space, even bit. If there's a carry, we just skip it. Okay, that's why you need here. This one was skip. And just keep this result. And this will be the answer by adding these two. This will be the correct answer. So we perform the tooth complement system. If there have a carry, a fifth space, in the n plus 1 bits addition, just skip it and use the remaining result, the original number of bits, the result of the final 4 bits, right? In this case, and this one is the correct. Okay. So the important pointer right here, if there is a carry from the side bit, which is 6 which is not the overflow, okay, and the answer will be converted. So if there is a carry from either side bit, the carry from the side bit, it is not overflow. Okay, it's the important point right here. Okay, and the case addition of two negative number, let us check. There -3 4. We also -3 is equal to this expression in the table. The -4 is equal to this expression, and the treat this two number are positive to perform the addition. So these two numbers we perform the addition. Okay, 1 plus 0, 1 0 plus 0 is 1 plus 1 is 0. We have carry, right? Carry right here, okay? And carry right here, 1 plus 1 is 0, we have carry. It means there's 3 1 right here, okay? And 1 plus 1 is 0, and we have carry, okay? And 0 plus 1 is 1, so there is 1 value. This is digital right here, okay? And there is carry. So whenever there is a carry from the side bit, we just ignore it and keep the remaining result by this correct. Okay. So the correct answer will that's carry. So it's carry from the side bit. Just ignore it. Also, so it is not overflow. Okay. So let's see a final case. We are okay. The case of for today. Okay. Addition for two negative numbers. For example, there's -5, 6. In this case, 5 6 plus 6 will become 11. The negative 11 will be larger than 8. So they will be overflow. Let's see. Okay. The result when it is not correct. Okay. This expression right here is -5. That's 5. This expression here is 6. Okay. We perform the addition again, the regular before. Treat it to number positive. Okay. So 1 plus 0 is 1. 1 plus 1 is 0. Here. Carry. Okay. The carry right here is 1. The carry right here plus 0 0 is 1 1. Add here become 0 and 0 carry. Okay. So 1 plus 1 is 0. Carry right here. Okay. And the tooth comer there's a carry from the side bit where you know it. Okay. Because we only have 4 bits, so this bit has no. Okay. So our answer will become 0 1 0 1. Oh, okay, fine. It is not correct. 0 1 0 1 is not -11. Okay. Because in this case, there's an overflow. Because for the correct answer, need 5 bits. But the decision will only 4 bits. So in this case, there is correct. Okay. There are some reason which. So here just why we ignore the carry from the side. The final answer will be correct. If the confusion is satisfied, the number is smaller than power of -1. Why the answer is correct? Then it's right here. minus A plus A plus B. A minus A will be the negative number, and then 2 is common expression. So you know equivalent to this expression, equivalent to this one. A negative A plus B will become right here. Okay. This one will become because 2 is common, the negative A will become the power n minus A plus B will become this one. So to calculate the result will become this one. And we ignore the carry, just throw away this value. If there are carry from the same bit, just throw out this value. So throw away the last carry is equal to subtract to the power n. So the result is B minus A by 30. That's a 2-point carry from the same bit, and we still have the answer. That's the reason this is okay. So that's all the material for this week. So we'll talk about what's compensation for their condition next week. That's all for today.